Okay, so let's begin. I'm gonna move some windows around here.
Isomorphism. Now the point is, again, he's not going to do both. He's only going to give him either isomorphism.
Okay, cool. So let's talk about first. Chapter 11 covers Diffie-Hellman. I wanted to make some announcements. There's going to be a slight change in the schedule for the next couple of weeks. The syllabus has been updated accordingly. We will be covering this week chapter 11 and 12 on RSA. And next week on chapter 13, 13 and 14, we'll be actually covering the last sections that we'll be covering out of the Cryptography Engineering book. We'll be switching over to covering several sections from an introduction to mathematical cryptography for the next 4 weeks of the course after that. And the goal there is to get the audience a bit familiar with some of the number theory and group theory that is sort of core to really understanding cryptography. So the emphasis in that 4 weeks will be a little bit less on implementation, a little bit more on building a sort of mathematical intuition. And then in the final several weeks of the course, we'll be covering special topics in zero knowledge, and I think we'll have a section in fully homomorphic encryption. But if there's demand for taking 2 weeks to cover zero knowledge, we could do that instead. But we'll get to that soon. So yeah, getting back right into it. So this week we're going to be talking about Diffie-Hellman. And the core insight in Diffie-Hellman is that it's easy to exponentiate some value, but it's hard to find the inverse of that operation. And so we talked about that, I think, a little bit last week. And the sort of like core primitive that mathematicians use to talk about the discrete log problems, usually the sort of concept of a group. And one of the places that the cryptography engineering textbook, I don't think does as well of a job as it could, is that it doesn't really quite give a very rigorous definition of what a group is. So just to give a quick bit of background, I've dropped some notes on quickly what a definition of group is, what a definition of a group is, and how you might think about groups going forward. And the sort of core intuition here is that you have a set of elements with some operation defined over it, often either addition or multiplication. You can take a multiplicative group and define a sort of vector space over it. And this is a bit extra, so don't worry if this goes over your head, but you can define a vector space over it. If you have a multiplicative group, you can say take arbitrary scalars from some field, and then you can define addition over the scalars and still have your multiplication over the group. And if that was sort of maybe a bit too high level, don't worry about it. But the main reason that we use groups here, and specifically cyclic groups, is that they give us convenient structures to define cryptography over. We can define them with a maximum bit length. The size of the prime that we're computing over is the maximum bit length of any element from the group. And we know that we can define a group with arbitrarily many elements by just choosing a larger and larger prime. And so the core properties of a group are associativity, that you can draw the parentheses however you like. You can draw them around A and B or B and C. Identity, that every group has exactly one element, that multiplication by the identity element always returns whatever other element you are multiplying by. For every element, inverses for every element, there is another element that the multiplication of element A by its inverse returns the identity. And finally, closure, that any two elements in the group multiplied together produce a third element that's also in the group. And so a very simple example of this is the integers under addition. And obviously, if you add any two integers under addition, you have a third integer, and there's an inverse for any positive number. There's a negative number in the set of integers, and you can add in any order, and you will still get back the same integer, regardless of whether you add 1 plus 2 plus 3 or 1 plus 2 plus 3. You still get 6. So all of these properties hold for the integers under addition, but sort of the insight behind why we're using prime fields or prime groups is that the integers under addition is a group with an infinite number of elements. So the number of bits that you might need to describe an element from the integers under addition could be arbitrarily many. You could need a lot of bits, basically. So instead of that, we kind of want our groups to be upper bounded in the number of bits that it could take to require or to describe an element from the group. And so instead of using the integers under the integers under addition, we typically use groups that are in practice we use elliptic curve groups, but a sort of stepping stone to elliptic curve groups could be considered the integers modulo some prime under multiplication. So the integers modulo some prime. Sorry, was there a question? I thought I heard someone speak up.
There are a couple comments just showing that the resolution's a bit difficult. So if it's possible to zoom specifically on the right panel, I think, would be helpful.
Okay. Yeah, we're running into the font size problem. Sorry, guys. Okay. Can I get a confirmation that it is better or not? Let's do.
That is much better. I'm able to read that. So.
Okay. Yeah, sorry about that. Cool. Thanks for the heads up. So yeah, I'll just hover here for just a second. So yeah, we will be covering some background on Diffie-Hellman and RSA today, and so groups are sort of the primary character in describing discrete logs usually. And it's worth noting that in a multiplicative group modulo a prime, the reason I say a prime field is that any multiplicative group modulo a prime is also an additive group with just one additional element. The same group is an additive group if 0 is included, because 0 is the identity of all additive groups. So moving along here, we'll be talking about groups today, and the main deal here is that basically all of the sections in chapter 11 are fairly fundamental to understand. I think section 11.7 on choosing a safe group is a little bit breezed through, but I'll try to give some intuition there. So the basics of Diffie-Hellman are pretty much just this. Alice is going to send some group element to the power of x, and if we agree that it is difficult for an eavesdropper to say, I can determine x by just seeing g of x, then we have that Alice doesn't need to authenticate this message at all. This message is fine as it stands. And in fact, unless Alice might not even have some way to authenticate herself. So this is sort of what a certificate authority does, is if Alice has a known public key, and I'm kind of jumping a bit ahead here, but if Alice has a known public key to some central trusted authority, Alice can issue a signature by the trusted authority that her exponent is in fact her exponent, and that would be how Alice would authenticate herself. But in this context, we're not really thinking about authentication too much. This is just to introduce the premise here, that Alice and Bob can obtain a shared secret that is x and y. G to the y to the x equals g to the yx, which is the same as g to the xy, because multiplication is commutative in this context. So this is the Diffie-Hellman protocol is this two-step protocol where Alice sends g to the x to Bob, or Bob retrieves Alice's public key, where g to the x is Alice's public key, and he exponentiates it to his own secret key, which is y, maybe this should be slightly better denoted. X is the secret key, G to the X is the public key, Y is the secret key, G to the Y is the public key for Alice and Bob respectively. And if Alice can inform Bob of her public key, then Bob can generate the shared secret, and likewise for Alice. So this is a perfectly secure way for Alice and Bob to say, choose some public value, i.e. G to the some power, where the some power is the secret key, and this should be reasonably familiar to anyone that's worked on public key cryptography before. The Diffie-Hellman assumption comes up, or the Diffie-Hellman or discrete log problem comes up pretty much everywhere in cryptography. It's a very common set of assumptions, and it's very convenient to work over because we have very useful algebraic structure that results from this. So in a nutshell, the takeaway here is that finding X given G to the X is hard, and this is a way for Alice and Bob to establish some shared secret K, where K equals X times Y or Y times X respectively. Or sorry, K equals G to the XY or G to the YX respectively. Though it doesn't really quite matter whether we set K to equal G to the XY or XY itself. Okay, so moving along here. One subtlety of the group representation of working in a prime group is that the group itself may be the integer is modulo some prime, but that does not mean the group has prime order. In fact, the group of integers modulo some prime will never have prime order unless p equals 3. And it's worth taking a moment to consider why the group will never have prime order. And this relates to Fermat's little theorem, which I think I might have mentioned last week. And that's because the order of a group, the order of a particularly this sort of group of integers modulo some prime is always going to be p minus 1. And just to remind everyone what the order of a group means, it means that if we take any element from that group and we take it to the power of the order of the group, we will get back just the identity element, or 1, in a multiplicative group. So an example of that is that if we say, come over here and take 2 to the 7, so let's take the group of integers modulo 7, and we can say that 2 to the power of 3 equals, let's say 2 to 3 equals 8, which equals 1 mod 7. So naturally, if we said 2 to the power of 6 mod 7, then that would be 1 squared, so that would be equal to 1 mod 7. And we take 3 to the power of 3 mod 7, that would be 27 mod 7, which is just negative 1 mod 7. And we can think of 6 mod 7 as negative 1 mod 7. So negative 1 squared, or rather 3 to the 6 mod 7, would equal negative 1 to the power of 2, which is just 1 mod 7. And those are two examples, but this is to say that if you take a group element to the power of the order of the group, where in the case of 7, the group order is 6, every group element mod 7 to the power of 6 will be just the identity element, that is 1. And you can often check if a group element is able to generate all of the elements of the group, that is G, in the previous example, 3 to the power of 3, or 3 to the power of the group order over 2 that was, equaled negative 1 mod 7. And the outcome of that observation is that 3 will generate the entire group of integers mod 7. That is, 3 to the power of 1 is 3 mod 7, 3 to the power of 2 is 2 mod 7, 3 to the power of 3 is 6 mod 7, 3 to the power of 4 is 4 mod 7, 3 to the power of 5 is 5 mod 7, 3 to the power of 6 is 1 mod 7, and no integers were repeated in that list. Moving on. Let's see. Are there any questions about groups before I dive into the man in the middle attack on discrete log or on Diffie-Hellman? Feel free to unmute yourself.
There is one question coming in the chat from Skalnov being typed out. So
Okay.
the question is, polynomials work similar as a group?
Yeah. So the way polynomials sort of work as a group is that you can encode a tuple of all of the coefficients of. So supposing that we have a polynomial with only one variable, let's say p of x, the coefficients of x to the 0, x to the 1, x to the 2, and so on are the elements of the group, right? And in particular, if we multiply two polynomials together, we might get a polynomial of higher degree. But if we consider addition over all of these elements, then we can obtain another polynomial of similar degree. This gets to a sort of more complicated question. We can actually define multiplication of polynomials to be a group in a similar sense to how primes work to define a group modulo the integers. There is a concept in polynomial operations called the irreducible polynomial. And this is a bit too in the weeds for, I think, what I want to cover in this particular course, but the premise here is that you can define multiplication of polynomials modulo some irreducible polynomial to obtain a group in the polynomials. But that's a little bit more in the weeds than I think we'll be able to get to this time around. Yeah, any other questions before we move on? I actually see RNO has asked, are large primes used for well-known curves simply Rabin-Miller tested? Or is there a non-probabilistic way to test these? There is no non-probabilistic way to test these. Oftentimes we're talking about primes that are at the low end of things. We might be able to get a 256-bit prime for cheap operations, but for naive finite field-based cryptography, as opposed to elliptic curve cryptography, we need bit lengths, thousands of primes or more, or thousands of bits or more. So the only way that you would conceivably test a prime that large as to whether it was a prime, you couldn't possibly compute all of the primes equal to the up to and equal to the square root of that prime. And the intuition for oh shoot, that was a question for last week. Sorry guys. Thanks. Yeah, that's a confusing bit about this chat format. Yeah, well, I mean, just to close the intuition, you would only need to compute the primes up to the square root and check if the integer in question was divisible by all of those primes. All right. So I'm going to assume there are no more questions on this section and move along. Yeah. Moving on to man in the middle attacks. So one thing that I mentioned earlier is that in this picture, Alice has no way of authenticating herself. That is, Bob has no way of knowing whether Alice is who she says she is, or if Alice is someone else. And the interlude about certificate authorities was to say that if Alice and Bob both trust a certificate authority, of which there are roughly 600 that the internet uses, to authenticate whose public key is whose public key. Without that, an attacker can sit in the middle and say, well, I claim to be Alice, and I'm going to intercept messages from Alice to Bob, and I'm going to intercept messages from Bob to Alice. And while Alice may send her public key to Eve, Eve does not need to pass that public key along to Bob, and she can choose her own public key, G of V. And so when Bob passes his public key, G to the Y, to Alice, Alice could just as easily reuse GV here. I think they use GW just for disambiguation. But the point of this is that in this way, Alice has done key exchange with Eve, and Bob has done key exchange with Eve. But because there is no authentication in this scheme, Eve is able to intercept and read all communications between Alice and Bob without Alice and Bob ever even knowing. So Eve pretends to be Bob to Alice, and Eve pretends to be Alice to Bob, and Bob and Alice are none the wiser. This is called a man-in-the-middle attack. And the main deal with man-in-the-middle attacks is that they're incredibly difficult to prevent without trusted authority. That is, Alice and Bob, having never met each other, have no way of knowing that they're talking to one another. So the only real recourse there is that Alice and Bob need to have some method of saying, I am Alice, and you can trust that. And the easiest and often only way to achieve that is that Alice and Bob have a trusted certificate authority that says, I am going to sign a message saying that this is really Alice's public key and this is really Bob's public key. And if they can do that, then Eve cannot intercept their messages and pretend to be Alice and Bob. And so the main takeaway here in man-in-the-middle attacks is that authentication is really quite difficult to do for the first time, and there really is no way for Alice to say, I authenticate that I am myself without a third party. But the absence of authentication altogether means that Bob and Alice have no real way of knowing who one another are. So there are other things that can happen that are problematic. Even if Eve is not able to intercept the messages altogether, Eve can, say, deny Alice's choice of generator by basically intercepting the generator. Let me restart. So if Eve is able to choose, in some regard, what the generator for the group between Alice and Bob is, then she can choose a number that actually generates a small subgroup. So the available space of secrets for Alice and Bob is represented by this exponent, x. So ideally we want the space for valid values of x to be many, say on the order of 2 to the 256 possible values that x can take. But if Alice and Bob can be deceived into using some value for g, where x can only take on a significantly smaller number of values, say 1,000,000, then Eve has succeeded at undermining. The protocol. And so how would Eve do that? Eve could do that by either A, saying that she could of course be a man-in-the-middle as before, or B, there could be an insecure implementation in the software used by Alice and Bob. And so Alice could be tricked into using an insecure generator if the software was not sufficiently savvy enough to check whether the group G generated a small subgroup. And just to give a quick bit on what a small subgroup actually means, it means that operations inside of groups can have a full can be the full group themselves. That is, in the example earlier, I gave 2 to the 3 is equal to 8, which is equal to 1 mod 7. That means that the order of 2 is 3. which is not the full order of the group, which is 6. So 2 is a smaller subgroup within 7 than 3. So the takeaway here is that there are sort of implementation reasons, or there are implementation failures that can occur if the software doesn't actually do every possible check, and it can often be quite difficult to get the full list of checks just by reading textbooks or papers or whatever. And sometimes new checks emerge. Oftentimes a zero knowledge proof is added to prove, for instance, that someone knows some exponent in, for instance, fully homomorphic encryption protocols or MPC protocols. If 2 and 7 are coprime, would it generate a smaller subgroup? So 2 and 7, okay, so Skonov has asked, 2 and 7 are coprime. While would it generate? Okay. So the answer to your question is that it kind of varies. It's not entirely random what elements are going to be coprime in your subgroup, but your best bet is to guess and check. 2 is not coprime to 6, and 3 is not coprime to 6, and the order of the group is 6. The other element that is not, the other element that is the generator inside 7, I think, is 5, if I remember correctly. It would have to be. No, it would have to be 4. No, it would be 5. So Skonov asked, why would it generate a smaller subgroup? The answer is shrug, guess and check is pretty much your best bet. So on to safe primes. This actually gestures very much at why we want to use safe primes for our groups. And the safe prime topic came up, I think, last week when I mentioned Sophie germain primes, which form primes of the factorization 2q plus 1, where q is prime. In a group where p has this 2q plus 1 form, say the number 83, 41 is prime and 83 is prime. So the smallest possible subgroup for an element in the set of elements modulo 83 would be 41, since 41 equals, or 41 times 2 plus 1 is 83, where both 41 and 83 are prime. So the piece here is that we can choose primes p, where prime p has a form that looks like this, and then we can have a small number of checks to say, is this element going, or we can have a small number of possible element candidate, or the number of choices for the subgroups of p is small. So we basically win out of this, that there should be no elements in the group that have small order. And keeping that in mind, sections 11.5 and 11.6 describe an efficiency boost to choosing a prime of the form 2q plus 1. If our prime p has to be of bit size, say 1000, as is not uncommon, if we say we want a prime of bit size 1000, then the value for q has to be at least bit size 999. But it might be the case that we only need q, or we only need a subgroup of size 256 bits. So if we wanted to speed up the computation in the group where p is prime and p has 1000 bits, we would want to choose Q of some value of 256 bits and change 2 to a much larger value, 1 of presumably 1000 minus 256 bits, so roughly 750 bits. So if we could obtain some value for n, where n times q plus 1 produced some prime, and n was some value of roughly 750 bits, and q was some value of 256 bits, then we could have a much smaller representation for the generators in the group Q. We could use only 256 bits to represent any element in that subgroup, despite the fact that the group itself requires 1000 bits to represent elements. And if that went over your head, the example here would be that 2 in the group 7 produces a small subgroup with only 3 elements, but 3 produces the full group with 6 elements. Scaling that up to a much larger group size, where suppose 3 generated a group with 2 to the 1000 elements, but 2 only generated a group with 2 to the 256 elements. We didn't actually have to represent the group elements in the full bit length of the integers. We can represent them simply as the elements that will exist in the group of 2 generating whatever subgroup it generates. Hopefully that made sense. Moving through here. This is a reasonable discussion. They do drop a mention to the legendary symbol. The legendary symbol is worth a lookup, but I think is going to be kind of a bit outside of the scope of this particular lecture. I think they kind of bring it up out of context in an unjustified way. It's a bit of a fun number theory deep dive if you're interested, though. So I think they basically discuss in this section using a smaller subgroup. I would invite you to read these sections, though I would say that sections 11.5 and 11.6 do skim over a lot of details. So if you don't entirely get 11.5 and 11.6, don't be too concerned. And then I think 0.7 is basically just a admonition to choose large primes. And then 11.8 is a great review of this chapter if you need review of Diffie-Hellman and choosing a subgroup and the other checks that are sort of implicit. So let's skim on to chapter 12. So before continuing, I see that there is some typing in the chat. I want to invite any questions before we move on. Okay. Why would you need to have the full group if you can use the subgroup? Yeah, that's a good question. If the elements are from the full group, the best linear algebraic attacks still will only work over the full group. And this is what I believe to be true. I have to say that I am working off of my sort of memory of how this attack works. Basically, the index calculus, which is the linear algebraic attack on group structure, exists for only the larger size of the group. But if you're using the smaller subgroup, then it remains basically intact. That is, the smaller subgroup is resistant to the attack if it is embedded in a larger group. And second, will there be any coverage of elliptic curve cryptography? Okay, so to answer that, let's wander back over to the syllabus. So in the syllabus, I had tentatively planned that we could cover some topics on number theory, do a discrete log review, and in week 11, talk about some topics in information and complexity theory, and talk about probability and signatures. If I think, I'm leaning that if we were to replace any of these, it would probably be the sections on information and complexity theory. So if there is interest in covering elliptic curve cryptography, we can definitely skip 4.6 and 4.7 and try to throw a week at elliptic curve cryptography. Let me know what you think about that in the chat. I think that both of these topics are reasonably interesting, and I think we could go either way. Let's see. See a little bit more typing, so I'll leave a couple more seconds. And okay, great. So let's move on to RSA. So I want to preface the discussion of RSA with a paper that is both amusing and worth a couple of minutes of your time. The RSA GTFO paper is a amusing and fair assessment of whether or not you should use RSA. I forget if I've brought this up before, but RSA is broadly considered to be both inefficient and hard to implement, and possibly insecure even if well implemented. There are just lots of trapdoors that you can fall through. The RSA GTFO paper is a sort of amusing read if you are in the mood for some cryptography comedy. In a nutshell, most cryptography avoids RSA at this point because it is not only difficult to implement correctly, but also reasonably inefficient relative to other things, including elliptic curve cryptography and elliptic curve Diffie-Hellman. So, on that note, RSA. What RSA does have to recommend it is that it is incredibly simple to describe at the high level. And that simple description hides a lot of complexity and potential failures of implementation details that hide in the number theoretic structure of RSA. But RSA's basic premise, as is now I think reasonably famous, is that it's hard to factor n into two large prime numbers. So for 2048-bit RSA, we would take two large primes of roughly 1024 bits, multiply them together, and our adversary would find it hard to factor them back out into one another. And the Chinese remainder theorem is a sort of central character both in RSA, in describing RSA, but also in describing attacks on discrete log and Diffie-Hellman, in that, as you may remember from our previous discussion, the order of the group of integers mod 7, for instance, is not actually prime, but prime minus 1. So the order of integers mod 7 is 6, and we can actually, as it turns out, treat the reconstruction of discrete log in each of the divisors of 6, as opposed to treating it as the group of integers mod 7. So the fact that the primes that the group of integers modulo some prime are not a prime order group is strong justification for why we use safe primes in cryptography, because we want our large we want large cyclic structure so that we don't sort of run into Chinese remainder theorem attacks. Moving through. So the Chinese remainder theorem is fairly central, and we'll be taking a second pass at some of the cryptography mentioned in this section in a few weeks when we come back to an introduction to mathematical cryptography, a lot of the characters in this chapter re-arise in chapters 1 and 2 of that book. So if the first pass over it is a little bit over your head, don't worry too much. But the Chinese remainder theorem basically just states a fairly simple result. It is obvious that we can compute, say, our two primes p and q in this instance are 7 and 5. It is obvious that we can compute 16 mod 7 is 2 and 16 mod 5 is 1. It is less obvious that given the values x mod 5 is 1 and x mod 7 is 2, it is less obvious that we can take that and turn that into some integer or congruence class of integers. So the way that we would do that is described by Garner's formula. And Garner's formula is just a closed form expression of how you would apply the Chinese remainder theorem. In fact, most often I usually just hear Garner's formula being described as the Chinese remainder theorem. So if you never hear Garner's formula, you might always hear Chinese remainder theorem, since they tend to just be grouped into the Chinese remainder theorem. And I think, yeah, they do mention that the Chinese remainder theorem is named that specifically because of a old Chinese text dating back to Sun Tzu. So I think this is the first time I heard it, I was like, that's a weird name for a theorem. It sort of asserts that there is only going to be one Chinese theorem about remainders, but I guess it's sort of an interesting history of naming a theorem after a bit of text from Sun Tzu. So just interesting trivia there. The exercises for this section should be helpful in maybe learning to apply the Chinese remainder theorem and some of the intuition around groups and subgroups that I've kind of skimmed over in this lecture. The generalization for the Chinese remainder theorem, the generalization for the Chinese remainder theorem is that we can treat the Chinese remainder theorem, or we can use the Chinese remainder theorem to basically break down group structure, whether it's an RSA group that we're working over. And the RSA group is the group of integers that are co-prime to P and Q, which should be almost all of them, or a group of prime order, a group of integers modulo a prime, which will have group elements of order some divisor of P minus 1. And there is a question exploring that in the exercises for this week. So multiplication modulo n. The book discusses in brief the Euler's-Totient theorem, or the Euler-Totient function, which, similar to groups, I wanted to give a little bit more background on the totient function, and I have managed to include a slight typo. Sparse background on the totient function. The Euler-Totient function is basically, the intuition here is that you can use the totient function to obtain the number of co-prime integers less than the value. So if the totient of n, where n is prime, is the number of co-prime integers less than n, then all of 2 to n minus 1 will be co-prime to n. So the number of co-prime integers will be just precisely n minus 1. So for any prime p, the totient function of p will be just p minus 1. This is not so for non-prime values. So for 6, all of 1, 2, 3, 4, only 5 is co-prime to 6. So I believe, or actually I suppose we don't count 1. So all of 1 and 5 are the entirety of co-prime integers to 6. So we say that the totient of 6 is 2. And this is useful for mainly the reason that it helps us calculate group order. So before, when I said that the order of the group G, if G was of the form integers modulo some prime, we said that that was equal to p minus 1. Well, actually, it's slightly more general than that. It's equal to the totient of p. And if p is not in fact prime, if p is just any value n, for instance, two integers or two primes multiplied together, where those integers might be prime, then the totient gives the order of that group. So in the case of RSA, our set of elements is the set of elements modulo PQ, where PQ is the multiplication of two primes, and the totient of PQ will be not precisely PQ minus 1, but P minus 1 times Q minus 1, since some properties of the totient function that are in the section's reading. So the takeaway there is that the totient function is a sort of interesting and worthwhile function to understand because it tells you the size of the group that you're working over, or the order of the group. I tried to leave some useful notes there for understanding that better. And finally, we get to sort of understanding how RSA works. We define RSA by choosing two large primes of P and Q. And if we say that the two exponents for our crypto system are the encryption exponent E and the decryption exponent D, then D is the private key and E is the public key. And we say that simply this makes sense because we want to choose D as the inverse of E, so that any element A to the power of E to the power of D should be just A mod PQ. And this is sort of how RSA ends up working. So yeah, and in fact, we're going to choose the value E times D needs to equal 1 mod the totient of PQ, but it is impossible for an adversary to calculate the value of the totient mod PQ if they don't actually know what P and Q are, because the adversary view here is just going to be that they see n, but if they don't have these factors of n, then they can't actually calculate this value, so they can't calculate D. Okay, so and digital signatures with RSA are basically just the perfect converse of encryption with RSA, where encryption with RSA was just encrypting by multiplication, or encrypting by taking A to the E. To sign is just taking A to the D. And this makes sense because everyone else can verify by observing that A to the D to the E is exactly just A. So encryption and verification and signing are basically two converse parts of the RSA algorithm that make it very convenient to understand by sort of a pedagogical perspective how to understand RSA. You encrypt by taking A to the secret, and you verify by taking the encrypted value to the public. You encrypt by taking A to the secret, or A to the public key, and you decrypt by taking taking the ciphertext to the private key, where I suppose D is private and E is public. moving along here, I think that's pretty much it for this section. The section goes a bit more into the details of RSA, but I think we'll leave 5 minutes here for remaining questions from this week's reading. We could also go over the exercises from last week if there are no questions. All right, a comment that the font size.
So there's one general comment to still increase the font size. So I'm assuming on the left side now with the notes potentially might be a bit small for some.
All right, is that seem
That looks around the same size.
okay?
And then the RNO has their questions.
RNO CRT is generally stated as applying any number of congruences x equals a1 mod n1 x equals a2 mod up to. Yeah. There almost certainly is a general version of Garner's formula. Oh. Yes, I am muted.
Okay.
CRT is generally stated as applying to any number of congruences. Is there a general version of Garner's formula that can compute a number given n congruences? The answer is yeah, probably, but I wouldn't actually know. If we think of the problem of solving the Chinese remainder theorem as basically a set of algebraic equations where you just substitute the answer from equation 1 into equation 2 into equation 3 and so on. There almost certainly is some general closed form expression for that, but I wouldn't happen to know it. Yeah, any other questions before we talk about exercises from last week? All right. The exercises from last week were fairly straightforward. The first question was basically just intended to give you a chance to sort of explore the premise of how entropy is constructed. Entropy is basically just the randomness of a system measured as a random variable. A random variable is a sort of probability theory intuition for a value that could be any of a set of values with some probability. So the way we think of entropy is a measure of randomness, so it is precisely the measure of how likely or how much we know about the random variable in question. And so the probability of each possible value that the random variable can take on, if all of the values are equally likely, then entropy is maximized. And this means that if we combine several streams of entropy, if the random variables are composed in such a way that the output is equally obtained as a function of each of those random streams, then the randomness for each individual bit is non-decreasing. So the takeaway there is that randomness in independent variables can only combine in additive ways. But if the streams are dependent on one another, if an adversary is able to control one of those streams, then we can come into a situation where the non-decreasingness of the combining two streams of randomness is invalidated. So I gave a brief discussion of non-cryptographic PRNGs and cryptographic PRNGs last week. Mainly the output relies on the difference between the uncorrelatedness of values. A PRNG may have uncorrelated random values, but a cryptographically secure PRNG will also have unpredictable values. So why can a C-spring be constructed from a block cipher? Because if you could predict the next block in a block cipher, ask the adversary, then that would mean that you could predict the plain text. So it's certainly unpredictable, and it's also uncorrelated because each block in a block cipher should be indistinguishable from randomness. Otherwise, the adversary could infer information about the plain text. I got a question? Or maybe not. Okay. Shuffling along here. So the computing 397 inverse by hand was just an opportunity for you to get some practice in actually applying the extended Euclidean algorithm. The extended Euclidean algorithm, recall, is how we compute inverses, and we can simply obtain that the inverse of 397 is 754, or I think negative 754 if I remember correctly. Yeah, negative 754. So if all of this makes sense, we can probably carry on to implementing stuff. And let's wander over here. So let's implement some stuff. Originally, I had defined the assignment to implement the extended Euclidean algorithm recursively, but as I recall, it's actually not that worth doing. The recursive implementation that I used was simply to define the extended Euclidean recursively over self, obtaining the inverse of the smaller of these two elements, which is B. So the extended Euclidean algorithm implemented in a recursive way should basically take a couple of steps, and I was a little bit frustrated that there wasn't a more elegant way that I could find to do this recursively. It ended up taking up 6 arguments, so I dropped the requirement that it should be recursive. The Miller-Rabin test is, I think we discussed a bit last week, is basically this algorithm for, you need to recursively say, or sorry, not recursively, you need to basically just do a couple of these checks, and the real sort of intuition behind the Miller-Rabin test I don't think is actually conveyed very clearly by implementing it, but I wanted to give an opportunity to implement the check for the primality check that we use in modern cryptography. Font size, thank you for the reminder. I invite you to review the code in your own time, but you should be able to find it in the notes for this week. And with that, I think we'll close for any further questions before we call it a day for this week, and I'll briefly preview what we'll talk about next week. Okay. So this next week will be our last week talking about cryptography engineering. I wanted to cover a couple of topics from sections 13 and 14 and a brief look towards section 16. Most of the rest of the book is either, I think, exceedingly concerned in sort of technical details or in specifically implementing private key infrastructure. And if you are looking at implementing private key infrastructure, the rest of the book is probably worth reading. But outside of the context of specifically working on PKI, I don't think it's that useful. So next week we'll be talking about the topic of replay attacks, key negotiation, in that the Diffie-Hellman protocol is not actually sufficient to be secure. We kind of need to wrap it in some protocols that make it possible for Alice to choose, Alice and Bob to agree on secure parameters. Otherwise, Eve can manipulate stuff. So we'll be talking a bit about key negotiation, which is sort of the meta topic of cryptography protocols, and how to prevent replay attacks and other nasties in your cryptography. And it's this fairly good sort of tautological example, or a pedagogical example of like how to implement a protocol that securely wraps around the cryptography so the adversary doesn't get to obtain more than they should. Finally, we'll be taking a light read of chapter 16, which I think has to do with, oh gosh, what were my notes? Yeah, the chapter 16 gives an intuition for clock-based nonces. So we'll be talking a bit about that too. It should be a reasonably trivial reading. There's not a whole lot there, but looking forward to giving that lecture next week. So thanks everyone for coming, and looking forward to seeing you all next week. And bye now.
Bye.
Thank you.
Thanks
Bye.
for the lecture.